Hey guys, welcome back to the Spaces Summit Stream 3. Yeah, we're going to do our very last talk of this stream already, guys. There will be some talks in the other streams after this talk, but for this stream it's the last talk. Before I'll introduce the next talk, make sure you check out the riddles on the website. Still some time to do them and to win some prizes. And the game that's on the site, and also after all the talks finished, so also from stream 1 and stream 2, there will be a pub quiz at 4 p.m. I will also be there, so you can join me over there. And if during this talk you have questions, you can post them in the Mentimeter. There's a code in the chat on the right side, where you can see the codes you have to use, and then you can post the questions. And if there is time, I will pose those questions to the presenters. And or you can go to our lobby, to our Google chat room, where you can post the questions or have some other discussions with your fellow colleagues. So the next talk is about the real-time sales dashboard. And when I joined Bol.com in 2013, so already 7 years ago, there was that old Oracle database, very simple HTML table, which was querying the LSM database for real-time sales data, and we were all watching that screen during the season. Then came a few guys who made a proper UI out of it, and now there are some young professionals who even made the next generation of that real-time sales dashboard. So they will guide you through that journey, the system behind the real-time sales dashboard. Where your order is visualized in the blink of an eye. So let's go to Marvin and Goos for their talk about the real-time sales dashboard.
Yes, hello everyone, thanks for joining. Me and Marvin will tell you something about our next generation real-time sales dashboard today. So first, let's give a flashback to that screen that Björn was talking about. This was the second iteration, Ankarama, which Michael Houthuizen and Mirko van Ede, I think, revamped and built a UI on. What you see in this dashboard is what is the amount of items that sold today, the amount of orders we did today, the current revenue we did, where is stuff bought, what is recently bought, what is the best sold product today, stuff like that. Which is obviously very cool. Almost everybody in the company was looking at this screen at the last 2 months of the year. So were we in 2019 when we joined. But there was one thing that we specifically didn't like about this dashboard, and that it was pulling data every 5 seconds. So every 5 seconds, it would go back to the backend, get some data, animate it to look real time, and then you would wait for 5 seconds for the next update to come in. And we thought that with some newer technology and with our 20% young professional development time, we could make this a full streaming application in which data is never read, it's always being pushed through the system. So with that ambitious goal, we three started. Eugene sadly couldn't join us today, but my name is Bekerom, software engineer, help me find me. Marvin is a software engineer in the app product. So we're going to show how the system works today is by taking a single entity. We have multiple entities in our system, but we're going to take you on the journey of an order. How does an order come into our system? How do we handle it? How do we stream it out? And how do you see it? But yeah, without further ado, let's begin at the beginning. This animated box is representing you guys going through the system. And first, we will go to our data loader system, which Martin will tell you more about.
Yeah, so first things first. We are the order, we are outside of our domain, and we want to get inside our domain. So what we have for that is some PubSub subscriptions. And those PubSub subscriptions are being subscribed to by a library we've chosen, and it's the library created by Volkan. It's called Reactive PubSub. This way we can reactively pull all the messages from our subscriptions. And we have multiple subscriptions. One of them is SOAR, and those are for the shop orders. Since we have multiple subscriptions, we created a pretty generic piece of code that we reuse multiple times. So let's dive into the code. So what you see here is Kotlin Code. You see here the start receiving method where we receive messages from our PubSub subscriptions. So what we do first is we have a puller, we create a puller, and we start pulling. And all this pulling is done reactively in the reactor context. But since we are using Kotlin, we were very intrigued by Kotlin coroutines, and we wanted to try that out. So what do? Is we create a bridge coming from the reactor context to the coroutine context. And for that, we set up our own pipeline. And the pipeline in this case is our cold flow. Within this flow, we are in a specific coroutine context that will be configured later on, but you don't need to worry about it here. So what we do here is we have a flow, the pipeline we want to execute, and we actually want to measure how long this whole execution takes. So that's why we create a utility function execute measured. But the more important part is this part. This part is the sync. This is where the receivable equable messages coming from PubSub, and we need to sync them into a handler. And we have specific handlers for specific subscriptions. And one of the subscriptions is SOAR set. So after setting up this whole pipeline, we don't want to have unbounded concurrency. So we set a specific concurrency limit with the excess buffer size that is coming from Project Reactor. This is the default buffer size from Project Reactor, but in Kotlin coroutines it was bigger, but it wasn't working for us. So we tuned it down again to the excess buffer size. So after setting up this whole pipeline and switching to the coroutine context, coroutine world basically, we need to start it off as well. So we start collecting the work. And this creates a specific coroutine scope that we have defined for a subscription, and we just start the job basically. So there goes the order. There's an actual order coming in. And since we have the order now in our system, the next step is we need to apply some business logic. So what we set as a goal is we want a daily sales email. We want to match the daily sales email. So at the end of the day, a daily sales email is generated, and this will be sent to you if you're subscribed to that. And we actually want the daily sales email mirrored in a real-time sales dashboard as close as possible. So that means there's some business logic. And the business logic is basically which order or which item should we not or should we save. And here's a big thanks to Petra Hoefs. She helped us out. She showed us everything related to the daily sales email, how it's generated, what the data sources are, and what the queries are, and basically showed us the business logic as well. And one of the business logic is some items are filled out, and this is being filled out by PCF. And PCF stands for Product Category Finance. So what this means in a nutshell is every global ID within Bolt.com has a specific PCF ID as well. And some items we don't want to save, because every item that we do save, we calculate the revenue, or we calculate the value within the revenue. But let's say the category gift cards, those are items we want to filter out. We want to filter those out of the order because there is not actual revenue being made. And so there are more business rules like that as well. So after applying all the business rules and the order is being filtered out and the items, we want to save them. So with the reactive connection we set up with the database, we reactively save it to the database. Once it is in there, there's also some stuff happening. So there goes the order, and the order goes from the data loader into our database. And Koos will tell you more about the database.
Yes, thank you. So the order comes into our database. First of all, I'm going to give you a little bit of context on our database. We're currently running a Cloud SQL Postgres database for this layer of our application, which is our Google-hosted Postgres solution. Prior to this, we were actually running Crunchy, and we recently needed to migrate. Crunchy is a self-hosted within Kubernetes cluster for Postgres. And the reason I mentioned this specific migration is because I think the way we have set up data migrations is a very nice way, and maybe people can learn from it. We're using Google Dataflow for this. And Google Dataflow is another project running in the Google Cloud, which basically enables you to link any Google data source to any Google destination. And all our data sources happen to have that same data in a BigQuery table, which is a big data interface in Google. We can query for all our source data from there, and then have Google Dataflow put it on a PubSub topic, which our application can then just handle normally, which allows us to always get the latest state of our sources, and we can load historical data like this. It enables us to disable backup functionality on our own database because we always have a more up-to-date backup basically from our data sources. So without going further into this sidetrack, let's go back to our order flow. So after we filter the order, this is the query being executed to insert an order into our order entry table. The reason I show this query is that this last line is very important to us. As I mentioned, we use PubSub for getting all our data in the system, and PubSub has an at least once delivery policy, which is important to think about because an order definitely comes in once, but it might come in twice. The PubSub doesn't make sure that it's only delivered once. It can be delivered multiple times. So, like I said before, we don't want to read from our database, so we needed to figure out a way to drop messages that that are duplicated, basically. Orders are immutable, so we use the actual order reference as our primary key, and then if something is inserted and there's a constraint conflict on the primary key, we can basically just drop the message. So after inserting, this trigger runs. This trigger is called aggregate to hourly table. And after every insert on that order entry table, we call this function insert hourly. What does that function do? That function tries to take the hour of this new order. It basically removes everything after the hour, and then the hour is the primary key of this order entry hourly table that we have. It's an aggregation table. We first try to update that specific hour by just incrementing whatever order information we got in. Then if that succeeds, so it's a successful update, we just return from the trigger and we're done. If it doesn't, if it's still running here, that means that it's the first order of an hour, so we have to insert into this aggregation table. So why do we even have this aggregation table in the first place? We could also aggregate for every update that we get, just aggregate on the full table and then send that through, right? Like this aggregation table sounds like it's overhead. So we thought us first as well. But then at some point we were seeing database deadlocks, and we spent some late Friday evenings debugging deadlocks on the database to eventually figure out, okay, these 2,300 database transactions per second we run on a regular basis can't handle doing all these aggregations because the aggregation just takes longer than a second. It's just too much. So we need some kind of cache. But how do you cache in a streaming application without having to do calls to a separate service? And this is the way we solved it. So we have an aggregation table in between. That was our solution. And now we have sub-millisecond throughput of orders, actually. It became super, super fast after that. So cool. We have this aggregation now. But how do we continue through to our other applications, to our front end, to our API without actually reading from this database, right? That is where our holy grail PG notify comes in. This is, without PG notify, I think this would have been But what PG notify is a native Postgres solution for doing asynchronous notifications over channels. You use this syntax to do it. You say notify on some channel name, this can be any string, and then you give a payload up to 8 kilobytes. What this then does, if you call notify on the sample channel hello world, this actually fans out trying to notify all channels, all processes, free that's like this. Here I have an example of what that looks like. So I'm using one single notify and then the world. So we have the as a trigger on any table.
Yeah.
Converts whatever you're doing on that table, so if it's an insert or an update, whatever you just did to that table, it converts it to JSON, and then it sends it over a channel called rtsng dot concatenated with the table name, with using that PG notify function that I just showed you. So how do we use this in that order flow that I just showed you? So after inserting or updating on our aggregation table, we call this notify function, and then that sends out a notification that looks somewhat like this. So on that channel, we send a JSON payload containing that current hour with what amount is basically the current aggregation of this hour. So this is basically what we send through, and then our API can listen to that, which Marvin will tell you about more. But first, a little note about resources, because I think it's pretty cool with how little resources we're able to handle every single order, every single cancellation, every single category update. We're only using 2 CPUs and 5 gigabytes of memory. And on the right here, you see that most of the time we don't even use half of it. And you can also see how flat it is. Like if you told me prior to this project that we would be able to do this, I wouldn't have believed you. But I think it's pretty cool with how little resources and how efficiently we were able to solve this. But without further ado, let's go back to our API, and Marvin will talk about that.
Yes, thank you. So now we need to make the step from the database to the API without actually querying the database. This database is quite big. We don't want to query it. We don't do a sum in the database. We just want to listen. So our API is also connected to the Cloud SQL database, of course. Cloud SQL comes in again, and it's like the centerpiece. It's the single source of truth within our whole application. So we just need to listen for updates. Shouldn't be that hard, right? So the listen and the notification feature is specific to Postgres. So we use AutoDBC again within our API. That is a separate deployable from a data loader, and it just executes a statement. It starts listening to a specific channel we have configured. Since you have multiple channels configured as well, we made this pretty generic as well. So we just give out a flow of notifications. And then we have specific handlers for that as well that create a specific notification instance that we need. So after listening, we need to open up the connections notifications, and then eventually a flow of notifications will come in. But as Koos shown, there are a lot of notifications, or a lot of updates actually coming in. So about 2.3K every second. So to lower the load on the API, we only need to listen to the latest ones. Because it is an aggregation and a full row, we don't need to know the previous values. We can just use the latest one. And the latest one is a full row, so no delta. So what we did here is we said on back pressure latest. That means that if there are more notifications coming in than our application can handle at a certain point, it will just drop the older ones and only keep the latest one, because the latest one is the most up-to-date one and is the only interesting one at that time. We don't need to process all the other ones. So the updates are coming in, and they're coming in all over the place. We have updates coming in from our aggregation table. We have updates coming in from our total orders or total items sold. And now we need a way to go from the API to our multiple front ends. So each client that is connected is its own front end and is its own connection to the API. But we don't want to query the database whatsoever, so we need a way to cache it within the API and eventually fan it out to the front end. So how do we get from API to the front end? Normally you would assume there will be a thing, let's say a REST API, where you can send a GET request to and say, hey, I want the latest order totals, and you get it back. But since we have the goal of keeping it within the blink of an eye, we wanted streaming. So we killed the idea of a REST API within our application, and we went for RSocket. RSocket is an open source protocol implemented in different languages as well, but we've chosen Java since we're running on the JVM. And we are very curious to this. So this is built on top of a connection layer, and on top of that, it's based on the reactive manifesto as well. So it fits our needs perfectly. So why did we choose RSocket then? Why does it fit us so perfectly? So we have our statement. As said in the beginning, with the introduction we had, your order is visualized within the blink of the eye. And the average speed of a blink of an eye is 100 milliseconds. So looking at the updates coming in, we see 2 milliseconds delay between updates coming in. So this is way quicker than the blink of the eye. So what did we do? How did we achieve this? What we do is we set up a streaming connection with the API. This means we open a WebSocket connection, and on top of WebSocket, we use the RSocket protocol. And this means we only have one single network connection. We don't have multiple connections. We don't need to reopen. We don't need to do more unnecessary handshakes. It actually follows the kernel rules quite nicely, right? So this saves us quite some overhead. And the other big thing is it's not pooling every X amount of seconds. So instead of having a new HTTP call going out, doing a new handshake, setting up a new connection every 5 seconds, we only do it once with initializing in the front end. And then we say, okay, we are open for updates, send us some updates. So what we then have is an incoming stream of updates, and those updates can be read separately, and you don't need to know the previous ones. And the cool thing about this stream, and because of it is with RSocket and the React Manifesto in mind, it is a stream with backpressure support. So as we shown in the API, we also drop messages there, and we only want the latest one if we are overwhelmed. So the thing is, the updates are coming in, but we don't want the front end to look overwhelmed, right? We only want the latest ones and one of the smoothest possible on maximum capacity. So the front end actually sends some information how much load it can handle, and then it will request the specific amount. And this means the API drops messages. So what we have here are 4 updates coming in on the top. So you have 4 colors, the green, yellow, red, and purple ones. And the bottom line is our front end actually requesting an X amount of updates. So what you see there is it actually can receive 2 updates. Boom, 2 updates are in, green and yellow are there. But then there is an update coming from the backend, the red one, but the front end didn't request it yet because we are not ready yet to process more. And then a purple one comes in, but we will use that because eventually later on we will request a new amount of updates, and you only see the purple one coming in because the red one is not relevant anymore. It's outdated, it's unnecessary. And to save this overhead, we just drop it. This means that a specific client, 2 specific clients can be out of sync. So since one client can maybe handle more load than the other one, they will run out of sync. But eventually, we have an eventual consistency there because eventually they will have the latest update of that specific hour and they will all be the same value. So piecing all of this together, you get the new real-time sales dashboard. So you saw the total flow of an order coming in through pops up in our data loader, the business logic being there in place to match the daily sales email, the database doing some smart tricks with the aggregation, and then the front end actually listening to it and fanning it out again with some backpressure support to the front ends. And once this is all done, there goes the order for the final last time, and you will get it in our real-time sales dashboard. So this is how it looks. And as you can see here, the numbers are updating. On the left, you see recently bought coming in. We have 2 top 10s by revenue and by items. And this is the dashboard we came up with. We want to do a quick shout out to Petra for helping out translating the business rules that were there in place for the daily sales email so we can match it. P2 for the designs, big thanks. It was amazing working with you. And Michael as well for giving us the room to improve it and helping us out with any questions we had anytime. So thank you guys. If you're interested, you can reach the real-time sales dashboard at realtimesales.bol.io. We also have a public chat room available. It's called RTS-NG public. And there you can leave any feedback, or if you have any questions, we're always available over there. And thanks for your time, and back to the studio.
Yeah, thanks guys for the presentation. I don't have any questions coming in, but I do have a question of my own when I was watching the presentation, because I noticed that you decided to put some database triggers in there, some logic in the database. So what made you decide to put logic in the database instead of keeping it all in use the Kotlin backend?
So we basically had to, because our database is fully optimized for writing data. So if our application would need to read somewhere, that would like really interfere with the throughput we had. First, we had some checks. We had some more aggregation tables, but before we had those, we really saw some like the throughput drop from like 2 milliseconds to like a couple of seconds because our database is so write optimized, right? So we kept looking for ways to keep it streaming, keep it pushing, and then we inevitably had to use some database triggers and functionality, which not always is nice, but I think for this use case it was a very nice solution.
Yeah, cool. So primarily for performance reasons that you tweaked, and it appeared that putting stuff in a database, using database triggers was a very good performant way to solve that.
Yeah.
Cool. Yeah, because I have some experience with Oracle and with Pale SQL, and from there I was really at some point allergic to putting logic in the database.
Yeah,
you might
can imagine.
You might have heard those stories, but in this case, I think it's a very valid use case to put it in there. Yeah, thanks, guys. No, still no questions, so we'll leave it at this. If you still have questions, you can put them in the Google thread, and Marvin and Goos will answer them there.
Yeah.
So yeah, thanks.
All right.